Thank you. The first thing I want to thank the organizers for inviting me here. This is my second time at ICTS, and it's always a great experience to be here. You might think that my title is misplaced here, and indeed, it is, but but I decided to speak about this anyway today. Maybe I have to tell you the history of, very shortly, the history of this paper that I'm going to tell you about. A couple of years ago, I knew nothing, almost nothing about cryptology, and my department was offered a position of a temporary position in algebra. It was founded by one of these big national research projects. And the condition was that the person that we would hire had to do with cryptology, because cryptology is something which is a main issue in my country now. So I thought about it a bit. I thought, well, I don't know much, but my colleague Norberto Gavioli, with whom I've been working for 30 years now, almost 30 years, is interested in cryptology, and certainly it's an application of algebra, so why don't we take it? And we hired Riccardo Aragona, who is a young algebraist, expert of cryptology, and then once the ball starts rolling, then it picks up speed, and after a while we had another position, a temporary position for an even younger person, Roberto Civino, and we started working on that. And I was surprised because in this environment, in cryptology, there is a lot of group theory, and much more than I thought. And what I want to do today is not really to convince you, but to explain, to motivate with cryptology some very interesting group theory problems that we were facing. So let me start my first talk about cryptology with just some definitions. The first part of the talk will be motivation, and I will speak more about cryptology. And then there will be results in group theory. So if you don't like cryptology, be patient. And okay, so I need first to start with some definitions. A block cipher, a cryptographic system, consists, first of all, of a text space. It's a vector space over the field with two elements, the field of 2 bits, really, either 0 or 1. And of course, every text can be encoded into a sequence of zeros and ones in a computer. So we will assume to have texts of a certain length. If a text is longer, you split it into parts, and our texts will be vectors in V. And also the ciphertext, after the whole process of encrypting it, we will get a sequence of bits of zeros and ones. So the second important item is a key. Now, a key is really a set for cryptographers. For the sake of simplicity here, I assume that the key is a subset of the vector space I'm using as a text space. It could be, in fact, it could be a set of one element, really. You can do everything with one key, and then you have a process to produce other keys from this original key. This is the secret part. This is the part that you don't want other people to know if you want to keep the secrecy about the content of your message. And the third ingredient is a an injective map of the set of the keys in the symmetric group over the space over the text space. Now, the text space nowadays is normally either, I mean, n is either 128 or 256, and so the symmetric group is really fairly large. The monster simple group is a baby with respect to these groups. So this is our setting. Again, I'm speaking about a set of keys because I want to ignore the process of producing several keys out of one. I want to say that at the end of this process, the permutations corresponding to the keys that are called the encryption functions should appear sparse somehow within the symmetric group. I mean, this very nice picture that I borrowed from Roberto Civino, who is the author of the nice pictures in this talk. The bad pictures are mine. So, this tells you that this is okay and this is not really. I want now to start with a little bit with some groups. I mean, we all know that we can represent V into the symmetric group by the right regular representation, which is regular, meaning transitive, and all the stabilizers are trivial. This image of the right regular representation is called T by cryptographers, and called also the group of translations. And it is well known to us that the normalizer of T in the symmetric group is the affine group. It's isomorphic to the semi-direct product of V with its automorphism group, which is GLV. All this is well known to group theorists. But the important thing is that for very good reasons, when we choose our encryption functions, the permutations corresponding to the keys, we should stay away from the affine group. And what I will show you is an example which I took from that Roberto gave me really again, which shows that very clearly. Look at this. Suppose you want to send a message on the this message, I mean, this one. This is a message that I receive very often from my son, but that is not encrypted. It's loud and clear normally. So suppose that, so this is not a good example. I mean, it's not a good, but suppose you want to encrypt it really. So what do you do? For the simplest and most naive thing that you can do is take some noise, take another set of bits, which is sort of chosen randomly, of the same size, of course. These bits are really, rather than zeros and ones, are black and white, but it's the same thing. And then just add it bit by bit, pixel by pixel, to your image. The result, so the addition is this operation. This is the cryptographers call it XOR. Let's say exclusive OR, and it's really the sum modulo 2 pixel by pixel for us. And clearly you get something which looks like very well encrypted, another picture of noise really, of nothing. Anything is, you cannot distinguish anything in that. But suppose you are so happy that you encrypt also the second image, the smile, and with the same key, with the same noise, and you get this, which is again very well encrypted. And suppose your messages are are intercepted by somebody who wants to read them and is not allowed to. Then he simply sums the two messages and the encryption disappears. And you get something which is different from the two, but certainly not very well encrypted. You can really read both messages out of this. So this is a sort of naive way to tell you why you want to stay away from linear, from the affine group when you encrypt, when you choose your keys. And this is the problem, because, I mean the problem, this is the main thing, because yeah, the thing that I have showed you is a sort of very rudimental example of what the cryptographers call the differential attack. You have two messages, that are one which is somehow perturbed, which is changed a little bit. And the difference, if you sum them, the difference is just the perturbation. And then if you encrypt that, you want that here, what you get doesn't have, it's really random, doesn't have anything to do with delta. If there is the least even probabilistic statistical way to read something here, then your encoding system, encrypting system is weak, and they want to avoid that. So how to make the very primitive tentative of encryption that I did before more efficient? They use layers. They encrypt by layers. So there is a machine that encrypts. And the idea is that you start with your message, and then you divide into small parts and apply something which is confusion, which is not at all linear, and mixes up things completely, piece by piece. The reason why I was explaining the reason why they do that piece by piece, because the confusion step is very expensive in terms of machine computation. And so they do it piecewise, but then they add a diffusion layer, a linear map that take all the entropy, all the confusion that you have created, and mixes up. So the confusion is now spread uniformly on the whole message. And then, at this point, they add the key. Now, this is called, at this point, this is called the round key. It's one of the keys you have produced from your original key with a process that I didn't describe. And you add it here. It can change at every step, because this round is repeated several times, 10 or 20 or 30 times. At the end, you get your encoded message. This is proven to be much more secure than the encoding that I did in the first example, of course. Well, yeah, this says simply that with respect to what I did before, they added and repeated several times this confusion and diffusion layers that at limited cost increases the entropy that you add to your message to encrypt it. Now the point is that there are many regular subgroups in the symmetric group over V, and many of them are isomorphic to V. We all know Cayley's theorem. You can embed every group of that order in Sim V. And so now we are dealing with all the regular images of V. And this is something that I add here with a proof, because it's something that everybody believes. All the regular subgroups isomorphic to V are conjugate. Now, when I was looking for a reference for this, I looked into books, and I couldn't find one. If somebody has a reference for that, please give it to me. There is the original paper by Dixon, in which this result is hidden in the proof of another result. So I decided to give the very simple proof here because it's nice. So suppose you have the right regular representation of any finite group G. Now we are in a very general context. You take any finite group G and you embed it with Cayley's theorem in the symmetric group. And then take another regular representation, another representation of G, which is transitive and in which the stabilizers are trivial. Now indicate by G sigma and G tau the images of an element of G, and let one indicate the identity of G as usual. Now we define a map phi from G to G by saying that to the element G, by sending the element G to the image of 1 under G tau. This map is seen to be a permutation. Yeah, because tau is regular. So the fact that it makes I mean, there is only one permutation of the type G tau that sends 1 to that particular element. So now you take G sigma, the image of your regular representation of an element, and this is made of cycles. They all look like the one that I wrote here. Of course, we know that very well. And if you conjugate, we know how to conjugate a permutation when it's written in terms of disjoint cycles. So you just apply phi to every element of the cycle, and you get a cycle of G tau. That's it. G sigma went to G tau through conjugation by sigma. By phi, sorry. Well, this is not at all difficult. This is first year algebra. But I thought to tell you here about that because I had difficulties in finding a reference for that. And that's okay. So now if we have our, oh gee, okay. Now if we have some, our translation group, then we see that the operation, the addition, the operation that the cryptologists call XOR of vectors is given simply by the translation. We all know that. And similarly, if we have a different regular subgroup of sim V, then we can define a different operation on V by saying that the result of this different operation on A and B is just A permuted with the to which the permutation tau B is applied. Now it's easy to prove that V circle is an elementary abelian group, and therefore it's isomorphic to V. Now I want to say a few words on this on the name of this operation circle, because this is a very weak connection to this conference, really. Circle is really the Jacobson circle operation, because you don't see it here, but when the image of tau is in the affine group, you can substitute matrices, and you have a product for matrices. You can substitute matrices to the elements of, you can send the elements of V into matrices. You have a product there, and you can construct the circle operation. And this is exactly that circle operation. So what cryptologists do, I mean, the problem now is we have seen that we want to be nonlinear when we encrypt. Should we worry about being somehow far from the other images of the affine group? Now, here I wrote GL plus rather than AGL, but anyway, you should read, well, I mean, you can put here either the general linear group or the affine group, and the picture is the same. I mean, we said we want to be far from linear. Should we be far from linear also with respect to these new operations, these circle operations that we have introduced before? And the answer is yes, really. Oh, here there is this picture by Roberto. Is very expressive. If now you are a crypto analyst, I mean, you are the enemy, and you perform the differential attack again using the new operation, the alternative operation, the circle operation. It may happen, or may it happen, question, that instead of finding just noise here, you find a gift, you find something which is useful for you to break the code. And the answer is yes. And this is work of Roberto. Now, this is a picture by him, and I don't want to explain too much about that, because the important things are the fact that this is published. This is an attack using the alternative operation. Now, and this is a toy encryption code, because it's only on 15 bits, which is very small. But the idea is that you create the confusion by a nonlinear function, all the same in this case. Then you apply your linear layer to mix the confusion, and then you apply your keys. You can choose randomly the keys. And what happens is that there are instances in which these choices give you an attack that fails when you use the XOR operation, the sum of vectors, I mean the standard operation, and succeeds, gets some information when you use the alternative operation. Now, the idea is that the idea that cryptographers have is that wherever you can find that something is not pure noise, wherever you find a difference, a good crypto analyst can start to break the code. So they are very worried about that. Okay, so we are worried about the other regular representation of our vector space, and this is a definition. The weak key subspace is just the intersection of the standard right regular image and the alternative regular representation we are dealing with. And this is clearly the set where the two operations coincide. Now, here we start with some theorems, really. And if we choose our other operation in as a subgroup, I mean, if the other image of V, if the other regular image of V is inside AGLV, then the dimension of this intersection is at least 1. And this is a result of Caranti, Dalla Volta, and Sala. And at most, n-2. It cannot be maximal. And this is a result of Calderini and Sala, a recent result of Calderini and Sala. So this intersection is non-trivial, and it's something you can deal with. And if you now assume that this intersection is as big as it can be, so of codimension 2, then what is written here, I shouldn't go into details here, especially because my time is anyway. Simply says that the differences are easy to compute, and And there are matrices that are linear with respect to XOR, to the standard operation, to the sum, and also to the alternative operation. That is a risk. If you use one of those matrices in your encryption as the diffusion layer, then there is the possibility that with respect to the one operation, the code is resistant, and to the other, it's not resistant, and then you are in trouble. So from now on, I will just, I think my motivation is finished here. I hope that I proved that our interest is in deciding how big the intersection of two regular representations of V can be. And our first, is it a particular case, this one? And yes, it is a particular case. Our first theorem says something which is interesting with respect to what we have seen before. Here, the assumption was that T circle was a subgroup of AGLV, and here we proved that if the dimension of the intersection is n-2, then the circle is a subgroup of AGLV. We call this group, this regular images of V that have such a large intersection with the right regular representation, 2MI subgroups, second maximal intersection. And it's clear that the analysis of the 2MI subgroups makes possible the construction of ciphers, block ciphers, that are secure, that are resistant with respect to many attacks, one for each circle involved. I don't like very much the circle notation because it's ambiguous. The T circle is really a conjugate of T, and the information T to the G, I mean, the description of the conjugacy is much more, it's much clearer for me as a group theorist as this, but this is standard, this is the standard notation of that the cryptoanalysts use. So, yeah, there is maybe I have time to just give an idea of the proof. The idea is to prove that an involution of the symmetric group that does not fix any of the cosets of the subgroup W of V of index 4 and centralizes sigma W is an affine involution, is in the affine group. This is a little lemma. This is not difficult to prove. And then we observed simply that if tau 0 is a 2MI subgroup, so a regular subgroup with large intersection with T, this is generated by two such commuting involutions, and therefore we are within the affine group. But now, this is something that I didn't do. I mean, to write these elements of the symmetric groups, a group in matrix form. We are in the affine group, so we can use matrices. Our paper is full of matrices, which I didn't put here. And so this is, again, a very light, very thin connection with the topic of this conference. But this fact that you can deal with matrices is important to describe our next result. So we have these 2MI subgroups. Now, you look at the CELO subgroups of AGLV, of the affine group. we all know how they are, how they look like. You take the regular representation of T and you extend it by the unitriangular matrices, and this is one CELO subgroup. Then the others are the conjugates, of course, this in AGLV. Now, every CELO subgroup of AGLV contains exactly one normal 2MI subgroup, normal in the CELO subgroup. There is only one regular representation of T, which is normal in sigma, and that has large intersection of codimension 2 with T, which is also normal, of course. T is not one of the 2MI subgroups. So, and also there is a sort of converse. If you take a 2MI subgroup, then you have a CELO2 subgroup of the affine group such that this T bar, the one you have taken, is the T sigma we have constructed. It's not a one-to-one correspondence. The same T bar can work for several CELO subgroups, but it's a very nice match somehow. Of course, I mean, once you do these things, they are interesting for a group theorist. But of course, I would never think of studying the intersections of regular subgroups if somebody didn't tell me that it was interesting. So yeah, of course, yes. Okay, so the next result is very technical. It uses a lot of representation theory, really, of matrices. And it's based on two ideas. One is that the CELO2 subgroups, as I said, are isomorphic to I said already the first idea, which is standard. And also another standard idea is that there is a canonical embedding of AGLV in GLn+1, 2. Okay, so you, I didn't put it, I should have put it here. The idea is that you create a matrix of size 1 more with respect to V, and you put a vector here, a linear transformation here, and a column of zeros here. Okay, this is a way to write as a matrix an element of an affine transformation. We use this to prove the following. Now, let T bar, again, be an elementary abelian subgroup of a CELO2 subgroup sigma of AGLV. Then any such subgroup. Then this is normal in sigma. We are not assuming that anything about the intersection. This is normal in sigma if and only if it is either T or T sigma. One of these two, there are only two possibilities. And the proof, which is very technical, consists essentially in showing that T bar is 2MI subgroup, that the intersection is maximal. Then our result before gives the theorem. As a corollary, every element in the normalizer of sigma in the symmetric group, clearly, if it normalizes sigma in the symmetric group, but is not in AGL, doesn't fix AGL. So it must interchange by conjugation T and T sigma. And as a corollary, we have this picture. We have this situation. If we take sigma, again, the CELO subgroup of AGL, of the affine group, and you take the normalizer in the symmetric group. So the normalizer in the symmetric group has over sigma has index 2. This is easy. This comes. I mean, the sigma in its normalizer as index 2. This comes from the preceding theorem, because everything outside permutes these two subgroups, T and T sigma. So if you take two such elements outside AGLV, then their product should fix, and you are in AGLV. So there is only one. So the index is 2. I've sort of proved in words this corollary, which is easy anyway. Point. And we get this other result, which is really somehow close to the result of Philip Hall, that says that the CO2 subgroups of the symmetric group are self-normalizing. And here we have that the CO2 subgroups of AGLV are self-normalizing in AGLV. Of course, they are not in the symmetric group, because they are subgroups of the large CELOF subgroups of the symmetric groups, and so their normalizers grow there. This is the last result I wanted to that is in the paper, and then but our interest in this situation is not finished. I mean, now we have these 2MI subgroups that are somehow corresponding to normalizers of CO2 subgroups of AGLV. What happens if we take the 3MI subgroups? Now, what we are working on is that they are connected to normalizers of CO2 subgroups. There is a very nice geometry that links the regular representations of V and the CELOF structure of the affine group and the whole symmetric group. And we are studying that. That's work in progress, really. I don't want to speak about that now. And then finally, the problem will be to bring back this to cryptology, which won't be really my business, because as I said, I am a newcomer in cryptology, but certainly we want to apply what we get. And then there is this, so now the general problem is to study the intersection of two conjugates of the affine group, because these are, for cryptologists, these are the dangerous areas somehow. So I hope that I gave you an idea of what I wanted to give you an idea. That is that I was wrong when I thought that cryptology is somehow far and applied with respect to algebra. There is a lot of algebra, a lot of beautiful group theory that I wouldn't have discovered if it wasn't for cryptology. And thank you very much. I think I still have early.